Welcome. In this session, we'll talk about phasors. So, what is a phasor? A phasor is simply a complex number that represents the amplitude and phase of a sinusoid. So, phasor is a complex number that represents the amplitude and phase of a sinusoid. Okay. So, phasor is a complex number simply that model is the represents the amplitude and phase of sinusoids. Okay, so what's a complex number? In the last session, we learned about complex numbers. We know complex numbers can be represented as a plus jb, which is called the rectangular representation, or we can also write the polar representation, where r is called the magnitude and theta is called the phase. So in this session, we'll learn how do we represent our sinusoids in this form. All right. So let's start. Let's start with a very basic sinusoid. Let's suppose our voltage V of t in time domain is given as Vm cosine omega t plus theta, where the Vm here is the amplitude of this sinusoid or cosine. Omega is the frequency and theta is the phase. Okay. So omega t here represents the phase. Then we add phase with phase. That's the total phase of the sine. Now here omega is the frequency of the sinus. Now we can write this sinusoid like this. We can say this is the real part of complex sinusoid Vm e to the power of j omega t plus theta. How? We know from Euler's identity, we know from Euler's identity, e to the power of j omega t plus theta is given as cos omega t plus theta plus j sine omega t plus theta, where cos omega t plus theta is the real part of this complex sinusoid and sine omega t plus theta is the imaginary part of this sinusoid. So in other words, Vm cos omega t plus theta is the real part of this complex sinusoid, right? So now let's break the exponent into two terms. So we can write it as real part of Vm e to the power of j omega t into e to the power of j theta. And this can be written as real part of Vm e to the power of j theta e to the power of j omega t. So our voltage is equal to this. So this can be written as real part of V e to the power of j omega t, where capital V is equal to Vm e to the power of j theta. So where capital V is equal to this, we can also write this in the, so this we know from the previous lecture that Vm e to the power of j theta is a complex number, and we can also write it in polar form as Vm at an angle of theta. So our V is equal to this. So we can write it like where V is equal to Vm at an angle of theta. What's Vm? Vm is the amplitude of this sine wave or cosine wave here, and theta is the phase. So V, which is equal to Vm at an angle of theta, model is the amplitude and phase of this sinusoid, and this is referred as the voltage phasor. Okay, so this is the phasor representation of the given sinusoid. In other words, if the voltage is given by Vm cos omega t plus theta in time domain, then it is frequency. This phasor domain representation is simply given by V is equal to Vm, which is the amplitude of the sinusoid at an angle of theta, where Vm is the amplitude and theta is the phase. So if we have to convert the time domain representation of a sinusoid to the frequency domain, how we do that? We simply write the frequency domain is simply given as not phasor domain representation or frequency domain. Later we'll see phasor domain is also referred as frequency domain. Is simply given as Vm at an angle of theta. So the phasor representation of Vm cos omega t plus theta is simply Vm at an angle of theta, which is a complex number actually. Okay. Right. Similarly, suppose if we have I of t equal to Im cos of omega t plus theta, then phasor represent of this current can be represented given as capital I, which is equal to Im at an angle of theta, where Im is the amplitude of this cosine wave and theta is the okay. So in phasor representation, simply we model the amplitude and phase. Okay. Now let's suppose if our voltage is given in terms of sinusoids. For example, if our voltage is Vm sine omega t plus theta, we know from trigonometry, we can write it as Vm cosine omega t plus theta minus 90. Okay, because cosine theta minus 90 degree is sine theta. Okay, so what will be the phasor representation here? Amplitude is Vm and phase is theta minus 90 degree. So what will be the phasor representation? Phasor representation of this will be simply V equal to Vm is the amplitude at an angle of phase. Phase is theta minus 90 degree. Similarly, if our current phasor, current in time domain is simply given as Im sine of omega t plus theta, and we know from trigonometry we can convert it into as Im cosine of omega t plus theta minus 90 degree. Then the phasor representation of this current is given as I capital I is equal to Im, where Im is the amplitude at an angle of theta minus 90 degree. Phase here is theta minus 90 degree. Omega here is simply the frequency. So from this you can check in the phasor representation, we drop the omega t part. We don't write the frequency. We drop the frequency part, simply we only write the amplitude and phase. Okay, so this is very, very important. So in phasor representation, if you look at the complex part, what we did, we suppressed the e to the power of j omega t part. So in complex part, we simply suppress e to the power of j omega t part from this complex sinusoid, which is referred as the frequency of the sinusoid, or we can say we drop the frequency part of the sinusoid. Okay, in modeling these sinusoids in terms of complex numbers, we simply drop the frequency. Okay, that's how we represent this. All right, let's take some examples to understand this concept. So let's suppose the voltage in time domain is simply as this is 200 cosine of suppose 50t minus 45 degree. So if you look at this sinusoid, the amplitude of the sinusoid is 200. Frequency omega here is 50 radians per second, and phase is minus 45 degrees. So what will be the phasor representation of this? So V phasor will be simply equal to 200 at an angle of minus 45 degrees. That's the phasor representation of this. Similarly, if the current at any time t is given as, so I of t is given by 5 cosine of suppose 100t minus 40 degrees. Here, amplitude of this cosine wave is 5, frequency is 100 radians per second, and phase is minus 40 degrees. So what will be the phasor representation of this? Phasor representation of this will be simply 5, that's the amplitude, at an angle of minus 40 degrees. Okay, so this is the phasor representation of this sinusoid or cosine wave. So phasor representation of this given by, okay. All right, so this is, we are given the time domain representation. We convert it into the frequency domain representation or phasor domain representation. Now later we'll see phasor domain representation is also called the frequency domain representation. This is also referred as the frequency domain representation. And next class we'll see that this is also referred as frequency domain representation. So we are given time domain representation, we convert it into figure. What if we are given the phasor domain representation? How do we convert it into the phase in this time domain representation? So for example, question is find the corresponding sinusoid to following phasors. First part is I is minus 3 plus 4j amperes, and V phasor, second phasor is V phasor is given as 8j e to the power of minus j 23 volts. Okay, how do we convert these into the time domain? Time domain equations or time domain representation of it. So first let's check the first. So I phasor is given as minus 3 plus 4j amperes. Now we can convert it into the polar form as, you can say this is under root of 3 square minus 3 square plus 4 square at an angle of tan inverse 4 by minus 3. So 3 square plus 4 square is under root of 25. Under root of 25 is simply 5. At an angle of tan inverse 4 by minus 3 is 126.87 degrees. So we can write the time domain representation of this is simply 5. That's the amplitude. Cosine of, since we don't know the frequency, we'll write omega t plus 126.87 degrees. This is the time domain representation of this phasor, the given phasor. Similarly, we are given the voltage phasor here. So the voltage phasor here is so V phasor is given as 8 j e to the power of minus j 20. Now let's first write it in the polar form. So we can write this as 8. Now j we can write as e to the power of j 90 degree, e to the power of minus j 20 degree, where j is equal to this. How? We know e to the power of j 90 degree is cosine 90 degree plus j sine 90 degrees. Now we know from trigonometry that cosine 90 is 0, sine 90 is 1. So 0 plus 1, j. So that's equal to j. So this is equal to j. Okay. So now bases are same power. So add. So we'll write it as j 90 minus j 20. So 90j minus 20j is 70j. So we can write it e to the power of j 70. That this we can write as, this is the Euler form, we can write it in the polar form as 70 degrees. Okay. So now this is our voltage phasor. Voltage phasor is 8 at an angle of 70. Since we don't know the frequency here, since frequency is unknown, so we'll write it as V of t is equal to amplitude is 8, cosine of omega is unknown, so we'll put it like this, plus 70 degree. Okay, this is the time domain representation of the given voltage phasor. This is the voltage phasor. We convert it into the polar form like this, and this is the equivalent time domain representation. So what we learned so far? What is a phasor? Phasor is simply a complex number that models the amplitude and phase of a sinusoid. Now we know how to write a complex number in polar form and rectangular form. So we started with the basic sinusoid in time domain. Then using some algebra, we convert it into phasor representation. Okay, then we solved some examples to understand this concept. Represent a phasor. Now remember from the previous class, the phasor in complex plane can be written like this. Suppose our phasor is voltage phasor. That's equal to 10 at an angle of 40 degrees. Suppose this, how do we represent this in on a complex plane? On a complex plane, we can draw it like this. We have real axis and we have imaginary axis. So this is real axis, this is imaginary axis on this complex plane. So if the magnitude is 10 at an angle of, suppose this is 10 at an angle of 40 degrees. That's how we represent a phasor on a complex plane. So this is our complex plane. And this is the representation of this voltage phasor V. This 10 represents the magnitude and 40 represents the phase with respect to real axis. That's how we represent a phasor on a complex plane. This is very useful for once we start with the RLC circuits. Okay, I hope you understood the concept. Let me end this session here. In the next session, we'll start with what happens to resistor, inductor, and capacitor in phasor domain.